Everyone. In today's session, we are just going to learn about the theoretical distribution, where we are just going to look about your binomial distribution and Poisson distribution, which is in your syllabus. Okay. So, though you actually in theoretical distribution, we have two cases. One is discrete distribution, and other one is a continuous distribution, where we have the discrete distribution categories like binomial distribution and Poisson distribution and geometric distribution. Whereas in continuous distribution, we have uniform distribution, exponential distribution, and normal distribution. So in this video, we are just going to focus about only the discrete distribution, and for you, the under your syllabus, we have only two cases like binomial distribution and Poisson distribution. So first, let me look at your binomial distribution. So before moving to the binomial distribution, let us discuss about what do you mean by binomial Bernoulli distribution, which is also called as a Bernoulli trial. So Bernoulli distribution is will have the following properties like the experiment should consist of n repeated trials, and each trial's outcomes will have exactly two mutually exclusive events, which is like a success or failure. Two mutually exclusive, which is not that exclusive categories like success or failure, and the success is denoted by P, and whereas the failure will be always denoted as Q, which is 1 minus P. And the trial by trial, it is a constant and it varies. Okay. So, and repeating n number of trials are independent of each other. So, if these properties are satisfied for a particular experiment, then we will say that experiment follows a Bernoulli distribution. Okay, so now let me define you the binomial distribution. A binomial distribution is nothing but a Bernoulli trial which can result in a success with a probability P and a failure probability Q. Then the probability distribution of a binomial random variable X is given by P of X is equal to X is NCX P per X Q per N minus 1X, where X varies from 0 to N. So the parameters of your binomial distribution is n and p. We will not specifically say q because q is coined over p. Okay, so the main thing you should know is binomial distribution is ncx p per x q per n minus x, and the x ranges is x is equal to 0, 1, 2, etc. n. So where these binomial distributions are applied, it has been applied in a quality control measures and the sampling process in industries where they have the scenario of classifying the items are defective or non-defective, and even in the medical cases whether the surgery is failure or success, because the binomial distribution follows the Bernoulli trial where the outcomes of the Bernoulli trial are two mutually exclusive outcome like success or failure. Okay. It not only in these two cases, wherever we approach with success or failure two category outcomes, this binomial distribution applies. And in this binomial distribution under your syllabus, you are supposed to derive with your what is your moment density function, by mean and variance. You know how to calculate the mean and variance as usual. Suppose the category how to find the mean and variance with the moment density function will be shown in this video. Okay, so you know the moment density function is nothing but your expectation of E per Tx. Okay, so expectation of E per Tx of the corresponding probability function P of x. So summation x varies from 0 to n E per Tx P of x. So according to this, the binomial distribution, it is NCX P per x Q per n minus x, and so that we are just going with an case of x varies from 0 to n. So we have x here and here and here. So we are just going to group the power of x, and n minus is associated b. So when you're just grouping it, it will become ncx p e per t the whole power x into q per n minus x. Now apply the range 0 to n. So where is your x from 0, 1, 2 until n. So now when I'm just simplifying nc0, we'll have 1. Anything over 0 is 1. Q power n minus 0, so it is q1. Ncx is nc1, sorry, nc1 is nc1 p e power t q power n minus 1. So till we'll proceed, and finally ncn is 1 p e power t the whole power n minus 1 q power 0 is 1. So this is nothing but the expansion of it, like q plus p e power t the whole power n. So finally, your mx of t, the moment generating function of your binomial distribution, is q plus p e power t the whole power n. Guys, you should remember this one, because with this we can find mean and variance very simple. Instead of, if you want to find a mean, you have to calculate expectation of x, and for variance you have to find expectation of x square. Then you have to use a variance formula, expectation of x square minus expectation of x. Okay. So even for MCQ purpose, you should know what is your MGF of your binomial distribution. So let me calculate here mean and variance using your MGF. Okay. So expectation of x is nothing but, we have already done with the property in the unit 1. What is the formula to calculate here mean using your moment generating function? Usually moment generating function is defined, is categorized with, denoted with mx of t. So this is your mean. Mean is nothing but expectation of x, which is the first derivative of your MGF at t equal to 0. So d by dt of your MGF is q plus p e power t the whole power n. And then after differentiation, we have to make t equal to 0. So let me go for differentiation. So differentiation of this one is n times of q plus p e power t the whole power n minus 1. Again, I have to differentiate with respect to t. So take this, differentiate with respect to x, we have this p e power t. Now substitute t equal to 0. So you will get it as n q plus p e power 0 n minus 1 p e power 0. So e power 0 is 1 always. So p e power 0 is 1. So it is n q plus p. This is like q plus p, and here it is p. We know that q is nothing but 1 minus p. So what about this is, just bring this one. It's a binomial case when it is like p plus q is equal to 1. So that's what it has been left as 1. So finally the mean of your binomial distribution is np. Now I have to calculate the variance, right? So I want expectation of x square. So that is nothing but second order derivative of your MGF and turning t equal to 0. So d by dt of, already we derived the first derivative, right? So substitute here np q plus p e power t n minus n e power t. So now we have to differentiate it. So these are all like np is common, so different have it. Now this is one variable with the t, and this is other variable with the t. So when two variables are with t, we'll use udv formula, which is nothing but udv plus vdu. So here they have been making this as v and this as u. So differentiate it with respect to v. So this is nothing but n minus 1 q plus p e power t n minus 2. Differentiation for this one is again p e power t. Okay. And differentiation plus here q plus p e power t. Yes. So differentiation of this is like, this is v, right? Differentiation, it is p e power t. We have to have u. So it is missing here, it is e power t. And next we have to go for differentiation of v du. V is as it is, and du is differentiation v per t is e per t. Now substitute t is equal to 0. So it is np n minus 1, same everything. It is e per 0, p e per 0. Again we have like e per 0. So there is the case here. So e per 0 is going to be 1, right? So it is q plus p e per 0 n minus 1 e per 0. So now the simplification, this will turn as q plus p, which is 1, and this is again e power 0 into p, so it is p, plus this is going to be your 1 value, and e power 0 is 1, so that is 1. So np n minus 1p plus 1. So just make a simplification, just multiply inside, so that you will get n square. Simplify here, it will get n minus p here, np minus p plus 1. So now multiply here, so you will have it like n square p square minus np square plus np. So this is here expectation of x square. Now I have to find the variance of x. The formula for variance of x is expectation of x square minus expectation of x the whole square. So expectation of x square, we derived it n square p square minus np square plus np, and expectation of x is np. So np the whole square. So this and this get cancelled. So finally we'll have a minus np square plus np, which when we are taking out the common, it is np of 1 minus p. So we know what is your n minus 1 minus p, it is pq. So your mean is np and variance is npq. So with this, we'll just move with the problems on the binomial distribution. So the first problem, when the four coins are tossed simultaneously, what is the probability of getting two heads and at least two heads? Getting two heads. So if my success is getting two heads, I'll just find it. The probability of x is equal to 2, and at least two head is probability of x greater than or equal to 2. So now here four coins are tossed, so n is equal to 4, and probability of getting head is the success here. So head is success is 1 by 2. So failure is 1 minus p, so it is 1 by 2. And what is your probability distribution here? Because here success and failure, so it follows a Bernoulli trial, so independent trial, so it is actually the binomial distribution. So ncx p per x q per n minus s. So probability of getting 2 get exactly is p per x is equal to 2. So substitute n is equal to the value 4 here, p and q, and x is 2. So 4c2, 1 by 2 the whole square, 1 by 2, 4 minus 2. So we'll get this 3 by 8. Similarly, for the probability of finding at least two hits, it is probability of at least two hits. So greater than or equal to 2. We have tossing four coins. Okay, x is equal to till 4. So probability of x is equal to 2 plus, because greater than or equal to 2, plus x is equal to 3 plus x is equal to 4. So apply n here as for your x is 2, 3, 4, and apply the formulas, and finally we'll get it as 11 by 16. So coming to the second one, the probability that the patient recovers from a disease is 0.3, and if 18 patients are affected from the disease, what is the probability that at least 10 survive? At least 10 survive is probability of x greater than or equal to 10, and exactly 10 survive. So that is the probability of x is equal to 6, and the probability of survival, that is 4 to 7. So it is like probability of ranging from 4 x is not equal to 7. Okay, so this is a discrete case, right? So the disease recovery ratio is given as 0.3, so the success is recovering. So it will be 0.3, and number of peoples here is 18, and your Q is the we know it is 1 minus V, it is 0.3. And binomial distribution 18cx, because n is 18, right? And cx, and success p is here it is p per x q per n minus x. So now we have to go for the calculation of probability of x greater than or equal to 10. So greater than or equal to 10 is the scenario. Then we have to go and find one cases we can find it like probability of x is equal to 11, 12, 13, 14, 15, 16 till probability of x is equal to 18. So you can calculate this one and you can add it. In other scenarios, I can go like 1 minus probability of x less than 10. So it is like 1 minus p of 0, because the binomial distribution starts from x is equal to, the range varies from 0 to n. So it is 0, 1 till n, because the values of calculation is 11 to 18 is little difficult. You can say that 11 to 18 are numbers from 9, only 9 values I have to calculate, but here is more values. But the numerical number is a little typical, right? It's 11 cx, 12 cx, q per. So on. So number instead of this, it is very easy to calculate 0 value, 1, 2, 3, and single digit number, right? So it is considered like this. It's not wrong in doing like this also. You can go for this way. And similarly, it is 1 minus p of p naught plus p of 1 p naught. We'll calculate, and finally we'll get it as 0.021. So when I'm just going for the next category of exactly 6, substitute x is equal to 6 and we'll get the answer. And survival between 4 to 7, so it is x is equal to 4, 5, 6, 7. So use it in the distribution function as x values are 4, 5, 6, and 7. So and compute the answer. So this will be the final answer. So coming to the next problem, in a large consignment of a bulb, electric bulb, 10% is defective, and a random sample of 20 is taken from the for inspection. Find the probability that all are good. So here my success is like uh, uh, here my success, yeah, all are no defective items, right? Here 10 percentage is are defective. So here defective item is coined as here success. So 10% is defective. So P is 0.1, Q is 0.9, non-defective, and all are good. So no defective items. So X is equal to 0. And at most 3 are defective. So at most 3. So P of X less than or equal to 3. And exactly there are 3 defective items. So exactly 3 defective items, X is equal to. So making use of N, P, Q in this formula corresponding to 0 less than or equal to 3 means 0, 1, 2, 3. Keep it in mind, when it's binomial distribution you have to start from 0. Okay. So finally we'll get it like the value of this thing on substituting with the binomial distribution formula. And similarly when X is equal to 3, substitute it, we'll get the answer as 0.1901. Okay. So coming to the next problem, again it is known that the probability of an item produced by a certain machine will be defective for 5%. Again my success here is defective percentage 5. So Q will be 0.95. If the produced items are sent to the market in a packet of 20, so N is 20, find the number of packets contained at least two defectives, at least two defectives, at least two defective in the sense that probability of X greater than or equal to 2, and at most two defective is less than or equal to 2. This is your second case. This is your first one, and this is your second one. And these are in the consignment of 1000 packets. So packets of 20, and it is for the consignments of 1000. So we have to first find for the packet of 20 and find it for the consignment of overall 1000 packets, and it's given as a binomial distribution. So if it is X greater than or equal to 2, as I said, we can go for instead of going and finding till 20, 3, 4, 2, 3, 4, 5, we can make it as 1 minus probability of X less than 2. So less than 2 is nothing but 0 and 1. Find the value. So we'll get probability of X greater than or equal to as 0.2641, and we have to compute for the consignment of 1000. So it is n 1000 times of your probability. This will become 264. For the consignment of 264, we have for the consignment of 1000, we have 264 count of at least two defective items. And coming to the next one, at most two defective items in a consignment of 1000 at most. So it is P of X less than or equal to 2. So it is 0, 1, 2, and we have to compute for the consignment of 1000. So in that scenario, we get it as 925. Is it clear? So coming to the next one, out of 800 families with the 4 children each, how many families would be expected to have 2 boys and 2 girls? See, you have to decide boy is a success or girl. You have to assume like which is your success, getting boy or getting girl. So here we assumed as getting birth of a boy is a success. So according to boy and girl, your success is 1 by 2. Similarly for Q is 1 by 2. And here are getting first one, 2 boys and 2 girls. So I assume X is equal to the success ratio. So success is boy, right? So exactly. Probability of X is equal to 2. So that's what X denotes the number of success. X denotes the number of success here. So exact 2 boys and 2 girls. So 2 boys, so P of X is equal to 2. And this is a binomial distribution where we'll write the binomial distribution. We know it is N C X P power X Q power N minus X. So you know N is 4 and P is 1 by 2, Q is 1 by 2. So that's here. And 2 boys and 2 girls. So probability of X is equal to 2, which is equal to 4CX 1 by 2 the whole square, and this. So it is 3 by 8. But here we have total 800 families. So I have to go and find in 800 families how many will have such a category. Possibility of such a category is 300 families. So 800 into 3 by 8. Similarly, at most one boy. At most one boy is maximum you should have one boy. So this second one will be at most 1. So probability of X less than or equal to 1. And at most 2 girls. So at most two girls in the sense that probability of X less than or equal to, because at most two girls means at most two boys. Consider both of the gender, children of both the gender. So both the gender in the sense that probability of X is equal to both the gender. It is like 1 minus probability of common gender. X is equal to 2 and 2. Okay. So let me explain here. So at most one boy. So probability of X greater than 1. So it is greater than 1. It's 1 minus P of X is equal to 0. So use it in the binomial formula and we'll get it as 15 by 16, and you have to convert it for the 800. You have to find it for the 800 families. So it will be 750. At most two girls. So at most two girls in the sense that we have exactly like at most two girls, 0, 1, 2, 3 girls. So possibility we can find it for X less than or equal to 1. So instead of that we can, yeah, that's what X at most less than or equal to 1. So it is like P of 0, 1, 2, 3 girls. So if it is 0 girls, it will have 4 boys. If it is 1 girl, we'll have 3 boys. And if it is 2 girls, obviously 2 boys. So it is like this calculation can be done either calculating like a P of 4, 3, 2 added, or else the same scenario I can say it like 1 minus P of 0 and P of 1, because we have the binomial for 0, 1, 2, 3, 4, right? So can find it for 800 families. Similarly, for the children of both the sex, so both the sex in the sense that we have to find like the combination of both the sex. But here when you are finding, we can remove the identical sex, like all are four, all four are girls, all four are boys. So that is 1 minus probability of all four are boys, all four are girls. Probability, because we assume there is all boys as success, we will take probability of X is equal to 4, and probability all are girls, that is X is equal to no boys, right? So X is equal to 0. So find it and find it what is the possibility about in 800 families. Okay. So the coming to the same second next problem in a binomial distribution, where the mean is 6 and variance is 2, you have to find the distribution. So if mean and variance is given, we can find what is the parameters like n, p and q. Solve these and we can find it like what is the value of your q, and once you know npq, we can write your distribution like ncx p per x q per n minus x, because we found it what is your q. Once we found q, we found what is your p, and we know what is, and based on npq we can find what is your. Substitute these things to find your value of your n is equal to, so n is equal to 9. So we know all the three parameters. So your binomial distribution will be this thing, and you have to find for p of x is equal to 1. So substitute it 0 point on it. So simplification, you will get 0.012. So coming to the next one. So we have a binomial variable x satisfies a relation n is equal to, it is given like 9 9 times of e of x is equal to. So it is like given the relation, it is 9 times of p of x is equal to 4, which is equal to p of x is equal to 2. And it's given n is equal to 6. So we have to find the parameter p. So you know what is your general binomial distribution, right? And they have given what is your x value. So substitute this x value on left hand side and right hand side. So and you know what is your n is also like 6c4 p per 4 q per 6 minus 4. So now make a simplification. Once after making simply power, here it is 4, so we'll cut off this one, so it is 2, and here it is 2, we'll cut off 2, so we'll have like this, and you have to compute what is your 64 and what is 62. So on simplification you will get like this, and then again simplify it, you'll get 9p square minus 9 q square, and simplify, because if the parameter is in the same two different parameter with a single equation we cannot find. So if it is a single parameter, we can find using quadratic equation, right? So make this q as 1 minus p. So simplify it, you get a quadratic equation, solve it, and you'll get the value for p. So when you're solving it, you get the values like 1 minus 2, 1 by 4. But the probability cannot be, the p cannot be, success cannot be negative. So the only possibility of p is 1 by 4. Okay. So similarly, the next one, the question in this question, they have given you the moment density function. From this, you have to find your expectation of x, variance, and probability of x is equal to 2. So it is like if this the given is mx of t. So mx of t is 1 by 4 plus 3 by 4 e power t the whole power 5. And you know, that's what I said initially. You should know the mx of t in general. So mx of t is this thing. So compare this and get what is your q, p, and n. So from this we can find variance. What is a variance? Expectation. Expectation is NP. So you know what is your N and what is your P. And variance is NPQ. So find it. And probability of x is equal to 2. You know the generalized formula. It is NCX, P per x, Q per N minus x. So accordingly find the value. Very simple. So coming to the next very important idea is fitting a binomial distribution, where you can expect this is near 8 marks question, like fit this distribution of the parameter, right? So, fitting a binomial distribution here, they'll give you the data. So, where this we'll be asking this follows approximately a binomial distribution. So, we are supposed to find the probability mass function. Okay, so we are approximately assume it's a binomial, and we have to find the probability mass function and finding the theoretical frequency of the corresponding. So, to find the binomial frequency distribution, we use this scenario, like we use this n into q plus p into the whole power n, the frequency, whereas for the given data. So for that we require with the n, capital N is total number of frequencies, number of trials, and here it is the success. So total number of frequency, we will add it and we'll get what is the total, that is here n. And number of trial is starts from 0 and ends in 6, so it is 6. So we have to find p. So we know that your mean, right? So if a data is given, we know how to find the mean. Mean is average. So make it a find as x into f, and add it and find the mean. So it is average, right? So your mean is x bar. You'll find it, and you know what is a binomial mean? It is NP. So equate this 2.4, and you know what is your n according to the problem? It is 6. So x terms of p is 2.4. So finally you can find it. What is your p? So based on p, you can find what is your q. So now I'm ready with my parameter npq. So now I have to go and find the theoretical frequencies. So it is like NP x is equal to x, right? So NP x is equal to x. So it is n. This is a corresponding probability distribution. NCX p per x, q per n minus x. So here it is like here n is known, right? So it is 80 and here n is 6. C, x may varies. P here it is 0.4 whole per x and q is 0.6 n minus x. So it is 6 minus x. So now we have the data from 1 to 0 to 6. So we keep on varying the range of x. So find for x is equal to 0, x is equal to 1, x is equal to 2, x is equal to 3, x is equal to 4, x is equal to 5, and x is equal to 6 finally. So we will be getting a numerical values in a decimals. So we have to make this to the approximation to the nearest integer. So it is 4 and it is 15 and it is 25 and it is 22. If it is 0.5 or 0.5 above, we will make it to the next integer, right? So it is 11 and it is 3 and it is 0. So now look at it. For 0 it's 4 and it's 15, it's 25, it's 22, 11, 3 and 0. So what's the beauty is when you're just adding these, finally the total frequency is distributed and total is 80. If it is not mismatched, check whether the approximation you made very correct. Is it clear? Yes. So with this, we'll end with the binomial distribution. Thank you.